I hate is the sound of a vacuum cleaner in the background. Okay, so we are actually going to apply our methodologies of general relativity that we've seen so far to real-life systems. Today is the first, namely black holes. And maybe we can start by writing down the methodology of the last couple of weeks that other people otherwise would have put on a slide. Okay? So there's many ways that you can recap relativity, general relativity, but there's one particular nice way of phrasing it that was by one of the main practitioners of general relativity. No, not Einstein, I mean Wheeler, John Archibald Wheeler. And he had a very nice way of phrasing general relativity. So let's take that statement and look at it for a couple of minutes, and then start to apply it to our case of black holes. Namely, according to John Archibald Wheeler, he said general relativity can be encapsulated by two statements. The first one being, what do you have to know? Maybe somebody did
matter tells space how to curve, and curve tells matter how to move.
There we go, okay. Statement number one, matter tells space how to curve. Statement number one, and of course by space we mean space-time. And then the second statement, I knew there was going to be at least one person who had seen this quote before. The second statement is, and space tells matter how to move. And this really is all of general relativity. Everything is in there. Of course, you have to put everything into formulas, but you know, those are just technical details. Now, it just so happens that for both of these, we have a formula, yes? Now, this one is the one that we spent the most time on last week. That was the famous Geodesic Equation. This one we also discussed, but didn't go through the full technical details. This is the Einstein field equation, the thing in which you put how much matter and energy there is in a particular region of space, and it spits out how space-time is curved. Now I'm going to write down both formulas. This is the Einstein field equation. We've seen it before, where this part, the right-hand side, is really just the amount of matter and energy and motion as well that you have in a particular region of space. That's given by this tensor here. The T is called the energy momentum tensor. And people who want to continue Lagrangian physics will get very acquainted with that thing. Okay. Now, then the left-hand side then spits out, if you solve this equation, your metric tensor. That's what the thing does. So this part, that first part by John Wheeler, matter tells space how to curve, is actually, you know, in phrasing it's quite simple. Somebody tells you how much matter and energy there is, and this equation then tells space-time how it is curved, because the curvature is all written in the metric tensor. That's all there is to it. Of course, solving this equation, this is the hard part. All right. One final comment before we go to the next statement. I didn't really put emphasis on this number before when we discussed this equation before, but it is a small number. There's a g in there, that's Newton's constant, 6.7 times 10 to the power minus 11 in your typical kilograms, seconds, meters units. 10 to the power minus 11, very small. And you have to divide it by c to the 4, and the c itself is 10 to the power 8. C squared, with the 3 in front, gives you 9 to the power 16, which is about 10 to the power 17. And you have to square that one more time, right? Because you have to get ultimately to a c to the 4, so it gives you 10 to the power minus 34, plus 34, so 1 over c to the 4 is 10 to the power minus 34. And then you have to make it 10 to the power minus 11 smaller still. So this number here is about 10 to the power minus 45. Well, that is a small number, okay? So start with a 0, you put a decimal dot there, and then you have to add another 44 zeros, and that is when you get your first non-zero number. So, so what does it say about the right-hand side of this equation? If this number is extremely small, a very small number times energy.
But energy doesn't have a huge effect.
That is exactly right. That apparently this is the whole right-hand side is about 0, right? And the only way that it's non-zero is when the amount of energy or mass has to be ridiculously big to compensate the 10 to the power minus 45. That thing has to be, I don't know, 10 to the power plus 45 or something like that, but it's a huge number to compensate. Now, guess what will come out of this equation if you put this to 0? We haven't fully studied the equation, so we haven't solved this equation yet, but suppose that you would have to take a natural guess. We put right-hand side to 0. What would you guess is going to be the solution to the equation? Minkowski's space-time, exactly. There's no coincidence. Einstein made the equation that came out. Okay? So it makes sense on all kinds of physical levels, because at the moment that you literally have no mass around, then you have nothing to curve the space. You have no gravity. So it makes perfect sense. But the fact that the number in front of the energy that you put is 10 to the power minus 45, so close to 0, means that, that in order to get some curvature away from Minkowski space-time, you need an enormous amount of energy. You could also say that the stuff of which space-time is made, the thing that you try to bend and curve, apparently is ridiculously stiff. You really, really have to press hard to make it, to give any kind of dent. That's what the smallness of this number physically tells you. Now, there should not be a huge surprise here, because you know that gravity is weak, right? I mean, sure, I mean, all of you are used to the fact that if you drop something, it will drop on the floor, so apparently gravity is very ubiquitous, yes. But note how much gravity you need, how much mass you need for your pen to start dropping. You need planet sizes of mass before you finally see some effect of gravity. Right? There's literally almost no attraction between all of our individual masses with respect to each other. There is some, but it's ridiculously small. So this is why if I drop the pen, I don't have to worry about it flying towards me or towards you, because that effect is there, but it's ridiculously small. Again, it's all the smallness of this number. I didn't fully emphasize that point before, so that's why I'm doing it now. Good. So this is the first part. Matter tells space how to curve. You solve this equation, difficult exercise, and you get your metric tensor. And if there's one thing that you should have picked up from the last 2 weeks, is that the metric tensor tells you everything that you need to know about the curvature of space. So once you have that number, you have everything that you need. Good. Now we're going to apply the metric tensor, because that's the second part of John Wheeler's way of describing general relativity. If you know how space is curved, you can tell how other matter, not the matter that makes the curvature happen, but other matter within that curvature, how that moves. Now, this, of course, is our geodesic equation. That we studied last week. That's the one. With the Christoffel symbol that I'm not going to find out. You should, well, you probably don't know it by heart, that's fine. You'll get it on an exercise sheet when you get your exam and such. But you do know that the Christoffel symbol here is completely dependent on the metric tensor. If you have been given the metric tensor, G mu nu, you will get the full Christoffel symbol, yes? We did some exercise on that. Somebody gives you your metric tensor, you can write down what these things are, and you can calculate by solving this set of differential equations then how in that curved space-time matter will move. And this is all there is to it. It's just the mathematics that is such a sucky exercise every time. So this really, really summarizes everything that we've done so far. Now it's time to apply stuff. Now I'm going to give you a metric tensor. Let me write it down immediately. This is the one we're going to work with this week. It is called the Schwarzschild metric tensor. Let me write it down first, and then we're going to discuss what it means, maybe what we can learn just from the expression itself. And of course, the application of this Schwarzschild metric test is, of course, exactly what will bring us to everything that we need to know. All right. The Schwarzschild metric tensor is given by the following.
What's the upper symbol? It's an M.
And that's an M.
Okay.
Yes, it is a mass. There you go. This here is the famous Schwarzschild metric test. You look very happy, Felix, for some reason. Why is that?
It's nice. It makes much sense.
Okay,
Is
tell
that
me.
a spherical coordinate?
Yeah.
Yes, it is a
Just
spherical
the
coordinate.
sphere.
R5 there.
But in the sphere, you have the first ones just being 1 because it stretches equally into all directions, and there
Here are your coordinates, by the way. Yes.
it's just, well, the time dilates and the space, well, it's the opposite.
Okay.
So it stretches out the further you go in, and then because you divide by the radius, it just becomes infinitely dark in the middle. So it's a black hole.
Okay.
It's nice.
All right, so there we go. There you have it, people. Everything completely solved. Now, Felix really did point out some very interesting properties of this particular metric tensor. One of the things that it immediately tells you, well, I'm going to just borrow a couple of the things that you dropped. I was actually planning on doing it later in the lecture, but now you bring it up, let's do it right now. So, indeed, what does happen when you make R infinitely big? Suppose you're going to be very far away from something. What that something is, we'll get there. But let's make R very, very big. What happens to this one here?
Basically becomes negligible. So
The whole thing?
No.
Becomes -1, right?
Oh.
And suppose if you do the same thing here, you make R infinitely big.
Becomes
Does it though? Really?
But it's inverted.
Yes. Yeah, I'm sure this will become
That's
infinity,
one.
yes, but there's a 1 minus still.
Yeah.
It's just 1.
It becomes 1, right? I mean, sure, this thing goes to 0, so you get 1 minus 0, 1, and then its inverse, which is 1. Well, these become big, but I have nothing to cross them out against. Okay, so these are just as they are. But if you recall from last week, the expression that you end up with if you just drop this one and that one is the Minkowski spacetime in spherical coordinates.
Yeah.
So you immediately saw that, right? This is what you were aiming for. So here's something beautiful that happens. Whatever this spacetime tells you, it tells you if you look at it from a very big distance, it will not look curved anymore. It will look like Minkowski spacetime.
But I mean, also in the middle, the time becomes infinitely big.
Oh, I agree. Yes.
The mass, like the space stretches out infinitely, so
Okay.
yeah.
Yeah, it feels right,
Yeah.
is what you're saying. Okay, well, of course, in real life, to make sure there really is a solution, you have to solve this thing. But yes, it also feels right. Yeah, I mean, you're right. Something else happens when you take your R and you take it to 0. Because then this becomes infinity. So that means your dt's become infinite. We have to think about carefully what exactly that means, and we will. And here, what happens here if you make R 0? This one here.
0.
Sorry?
It becomes 0.
It becomes 0. So whatever is going on here, you can see that the amount of duration between two events apparently very close to whatever happens to be at R is 0 becomes infinitely big. Yes? But distances seem to become infinitely small. We have to think carefully exactly how this is done. We will, of course. But you can see some beautiful stuff is happening here, okay? By the way, this M here, we identified it as mass because, I took the letter M. The M over there, what happens if you put M to 0, regardless of where you are, what your R is?
You go back to flat.
And that's exactly right. Apparently this M has whatever property it has, or whatever the thing is. Yes, it's a mass, because you can, I used the letter M, so I already gave it away, it's a mass, sure. But the fact that you that you can see that if you make these M's themselves 0, you also get a Minkowski spacetime. So what we have here is a situation, a metric tensor, that tells you there is something here-ish, and it's characterized by this letter M. Let's pretend we don't know that it is a mass. And if you're very far away from that mass, your curvature becomes Minkowski again. You will lose all effects of gravity. At the same time, even if you get very close to this thing, but this property itself becomes 0, you also lose all effects of curvature. Now that alone will give you a very strong hint that what you're looking at is mass. Okay? Now, one of the exercises for the tutorial is to make this argument a little bit more strong. Yes?
Sorry, why would that hint at the fact that this point actually mass density?
Because of Newtonian gravity, you know that gravity becomes increasingly strong when you get close to the thing, or becomes very small when you make the mass very small, or if there is a huge mass but you happen to look at it from infinitely far away, you will feel no gravity, or asymptotically no gravity.
But would there not be something else, like a charge or something?
Yes, there could. I agree. Hence, exercise in tutorial, to make that argument more strong. So I did not say this is a full proof. I'm just saying that there's a strong reason to believe that this is mass. All right. Now, so we can sort of already understand what the metric will tell us, right? Now, before we go into full detail, how did people get this metric to begin with? Yes, they solved this equation. There's a fun story involved there. Namely, Einstein, when he published the Einstein field equations in the winter of 2015 going on 2016, he solved it, but only for approximate situations. In fact, that's one of the exercises as well for the tutorials this week. What if you look at something that is curved but not extremely curved? Yes, and when he did that, he actually found the motion of the planets around the sun, he found the curvature of the light rays when they moved around the sun, these sorts of things. But he only did it in an approximate fashion, and he said, you know what, that is actually good enough. Has to do with the smallness of this number again. So, he actually said, Einstein, that this equation is probably too difficult for anyone to ever really solve, to get a full solution for it. It was in the December of 1915. Okay. Literally 3 months later, Carl Schwarzschild came up with this particular solution. He could actually show this is a not approximate solution, this is a full solution to this equation under the assumption that the thing is 0. And now I'm waiting for somebody to comment.
The whole right-hand side is 0.
Yes.
Mm.
Not
So that would
approximately.
imply that mass is 0 too.
No.
Oh, it's not the densities.
That's
I
strange,
mean,
right?
if the right side 0 should give you directly flat
Minkowski,
Minkowski
yes.
spacetime.
So you can see that it looks as if I stated two things during this lecture already that are contradictory, because at some point I said, well, if the right hand side is 0, the outcome is Minkowski spacetime. But now I'm saying, no, or Schwarzschild is saying, rather, no, you could also have this, what we now call a Schwarzschild spacetime. So which one is it? So if you make right hand side 0, apparently you have two solutions, the Minkowski spacetime, non-curved, and this new spacetime that is highly curved if you get close enough to the mass in the middle. So which of the two is the real solution, or maybe both of them are, or maybe none of them are? So I'm just curious whether you can understand if there is any discrepancy here.
Maybe they're both solutions.
Yes. But then begs the question, how many solutions does an equation have to begin with? It's not uncommon to have an equation have multiple solutions, right?
I mean, one could be the maximum, one could be the minimum. Since
The maximum in what?
you end up taking, it's a differential equation.
Yes.
Oh no, that doesn't make sense either. I was thinking one could be the maximally curved spacetime, one the minimally curved spacetime, and then you'd end up with, well, flattened black hole. But I don't think that works mathematically.
There's a lesson here. Differential equations in general have multiple solutions. Yes. Now, I'm not even going to go into the fact that this is a non-linear differential equation, the one that you can solve here, because it comes with all kinds of mathematical complications. Even linear differential equations come with multiple solutions. Now let's stick to the linear for now. Do you happen to know from one of your other courses, maybe electrodynamics, how many solutions a differential equation has? A linear differential equation. For instance, Maxwell's equations, just taking a random example.
I mean, you could always add some gauge or something like that to the
Yeah, because
Yeah.
of the
So if-
integrating constant. That's why you can shift it up.
Okay, no, that is of course true. If you solve the differential equation, you will get a solution that comes with integration constants, constants that you still have to supply numbers for. The mathematics doesn't know about these numbers. You, from physics, have to tell what these numbers are, right? I mean, in normal Newtonian gravity, you throw your pen around or something like that, you get a solution if you solve F equals m times a, and the solution will typically come with two unknown numbers. And usually what you say is, well, the initial velocity of your pen and how high it was when you threw it or something like that. It's the initial position. And you're probably used to this in all kinds of topics. If you solve a differential equation, you get a solution, mathematical form, with some constants in there that you still have to supply numbers for depending on circumstances. Now, if I leave out those numbers, I mean, they're still in there, but this is not the point that I'm looking for. Because even for different sets of numbers, the mathematical form of the solution will still be the same. My throwing the pen around will be a parabola. And how wide or high the parabola is, well, that depends on the numbers, but the answer is still going to be a parabola. My question is, are there other solutions possible except for the parabola? Do you have difficult mathematical solutions, not just the numbers within this mathematical form, the whole solution itself?
Yeah, apparently,
Yeah, well, you can see here that possibly that happens, right? And the answer indeed is yes, and not just because of this example. Yes, if you have a partial differential equation, partial differential equations have usually a whole set of solutions, usually infinitely many. So the form is completely, well, up for grabs. What you usually have, if you have a partial differential equation that you solve, is that maybe the form of the solution, the parabola in my metaphorical example, might be different, but the way that your solution, your form, depends on the parameters, space and time for instance, that particular combination is fixed. This sounds very abstract, I realize that. But I'm going to take my example, all joking aside, from electrodynamics, because it is such a good example. In fact, or from optics, whatever you want. That if you'll have the second derivative with respect to time, usually comes with a velocity there, and you have minus the second derivative with respect to space, then the solution, this one, will have many, many different forms. F could be whatever function you want, under the condition that f, which is a function of x and t, is only allowed to depend on x and t in this particular way. Right? So the shape is completely up for grabs, but the way that it depends on the parameters, that is fixed. Now, this is an example from optics, and yes, we also saw this during our electrodynamics course for people who were there. On the underlying message here is you should not be surprised if you have a partial differential equation that it comes with very many different solutions. So the same thing here. This thing with 0 on one side comes with many different solutions. Now, what differentiates the one solution from the other solution, I mean, what is it, which of all these many solutions should you pick, is dependent on boundary conditions. It's dependent on the physics. Take my example for the wave equation here again from optics, say. What shape is that? All these shapes are allowed. Which of all these shapes is the one that's actually used by nature? Well, that depends on how in this particular case, this electromagnetic wave was formed. If you have some physical context in which it came out as a sine function, then it comes out as a sine function. It's a very particular sine function because it has to depend on space and time in this particular way. But the fact that it is a sine function is context dependent. I'm sure that if you wiggle your electrons or your magnets around in a very particular way, you can make this come out a parabola, but not just any parabola, it's a parabola that depends on this way of space and time. Same thing applies here. One equation. Now, which of these solutions comes out is context dependent. Yes?
So I mean, to interpret our metric tensor to find which way an object travels, we also have to solve the differential equation. And you were saying that metric tensor holds all the information, but that would mean that the information which which solution of the differential we choose is still up to us now.
Yes. What I said
But
was.
how can we know which one to choose once we solve them?
That's, no. You first, when you look at this equation, what you don't do is first solve for metric tensor and then say what the context is. You take the equation plus its context and then you get your metric tensor. So once you have the equation and the context in which it should apply, that then specifies what the metric tensor is.
Yes, but then afterwards when we solve the negative one with the Christoffel symbol,
Yes.
then that's once again a differential equation that can have multiple solutions.
Yes.
Right? So how do we know there? Which
And,
one to choose?
oh, okay.
That's sorry. if
No,
I
no, I know.
misphrased my question.
That's a good point. You moved from here to here. That this is too a partial differential equation.
Yeah.
So that too comes with multiple shapes and forms. Yes. And there the same thing applies. It's context.
Okay, so yeah.
Right?
And where do we read the boundary conditions?
Sorry.
Where do we read the boundary conditions?
What do you mean? Where
Like
do you
mathematically speaking, how do we see them? How do we see?
in this here you're not seeing them because I did not write them down. I never specified any context. In an exercise, it's fully fixed. Yeah. They're literally watering the plant right now. No, but I'm just wondering how often can you vacuum the same little piece of carpet? And it turns out there is a guy, I just saw when I was looking out, there's a guy who's watering the plant with a hose from the first floor. And of course, 90% of the water does not hit the plant. So there's another guy vacuuming the excess water. I'm not joking, that's literally what they're doing.
I mean, use a hair dryer.
Oh yeah.
Yeah, it's not a vacuum, it's a dryer, I think, right? Or,
Because there's dust underneath stuff like here or something.
anyway, so then the question, of course, is what context does this solution hold? Because this is really Giovanni's question. I mean, where do we see the context here? I never wrote it down, so I'm giving it to you right now. Back to Schwarzschild, 3 months after Einstein published this one. Schwarzschild looked at the question, now what if you have a mass distribution somewhere in space, but the mass distribution is spherical? So whatever the mass does, the mass should look the same in all directions from a particular starting point in the middle. So this could be, a typical example would be a solid spherical ball, like the Earth. It could also be a spherical shell, right? It does not say that it has to be homogeneous, as in the same amount of mass at any point in space from any direction. It should be isotropic, is what I'm saying. It should be spherically symmetric. You can even have something, a spherically symmetric mass distribution that changes in time. For instance, you can have a, I don't know, one of these balls that you take to the swimming pool so you can throw it to other people and everything. If you blow it up, it will increase in size, but it will still be spherically symmetric. Now, Schwarzschild took that as the boundary condition. He said, I'm going to look for a solution that agrees with spherical symmetry. For some reason, the door just won't stay closed, so I literally locked the door now. So if there's any fire and everything, blame me. Okay. So he took as the boundary condition, I'm looking for a solution that has the property that it agrees with spherically symmetric distributions of mass. And then he found this. Now you might say, wait a minute, but if I have the situation where I have no mass, that too is spherically symmetric, you would be right. If there's one nice thing about the Minkowski spacetime is that you can, at any point, look in any direction and see exactly the same. So it's spherically symmetric, it's spherically symmetric plus, right? If you have this big ball, then the only way that it's spherically symmetric is if you yourself happen to be in the middle of the ball. Any other position in that space-time will break your spherical symmetry. Minkowski space-time has the property that it doesn't matter where you stand. Any point in space will have spherical symmetry. So you would expect that this solution should encapsulate the Minkowski space-time at the moment that you would remove the mass. And it does. That's exactly what we checked before. So we really have a solution that we can understand, and mathematically why we have multiple solutions, and also why it reduces to Minkowski space-time. So there you go. Now, sad anecdote. Einstein said nobody will ever solve this equation. It's just too hard. You can only at best find approximations. Then Schwarzschild 3 months later came with the first solution. This is what we now call the Schwarzschild solution, or Schwarzschild space-time, Schwarzschild metric tensor. And he published it, and he's now famous for it. It so happens that there was another guy who also came up with the solution before Schwarzschild did, even sooner than Schwarzschild, so 2 months or so after Einstein said that nobody would ever solve this equation. It happened to be a Dutch person named Droste. Droste was a PhD student of Lorentz, of the Lorentz transforms and such. And the Lorentz gauge, you know, not the Lorentz gauge, that's a different Lorentz, but the Lorentz of electrodynamics and relativity and all these things. Won the Nobel Prize for the Zeeman effect, that Lorentz, big Lorentz. And his PhD student, Droste, also found this solution before Schwarzschild did even. So he gave it to Lorentz and said, look, I found a solution. Can you say whether this is publishable? I should do something with it. It just so happened that Lorentz, the professor, was on a cruise. He was actually on a ship. You have to keep in mind this is 1915, so people did not take planes to other countries. He was on a ship. And of course that took weeks before he got from one end to the next. So Lorentz did not see his students Droste's solution for, I don't know, a month or so, or 2 months or so. He was laying on his desk collecting dust. Okay? In the meantime, Schwarzschild also came up with this thing independently, and he published it. So, poor Droste. So if there's any lesson from history here, if you have something that is worthwhile, do not wait for supervisors to look at it, okay? Just put it on the internet or something like that. You have to be a little bit careful there. You might also put there something that you wish your PhD supervisor would have looked at because it was crap. So there's a thin line here, but there's a lesson here. Now, this is still what we now call the Schwarzschild solution. Now, we can apply it in many ways now. The first thing that you can do here is that you can calculate the Christoffel symbols, and that you then can calculate how things will move in that space-time. And that's exactly what we're going to do for a couple of examples, and other examples are for the tutorial to work at. But before we do that, I think it's going to be worthwhile to write out the metric, the line element from this metric, and look for its properties. Okay? There is something in there that we haven't fully discussed yet, and this is a very good example to discuss this with. And it has to do with the fact, if these are the coordinates, which observer is actually measuring these coordinates? Let's go back to special relativity just for a second. In special relativity, you know that there's one person's time and the other person's time, or duration I should say, and they're related by to each other by Lorentz transforms, yes? And then one of the questions was, okay, but whose time is this and whose time is that? That was a question that you always have to think about if you did your exercises. The same question you can ask here. We have an amount of time here, but whose time is that? I mean, think about this. You have this big ball here that curves space-time by this amount. And I can place an observer here. Here's the big ball. I can place an observer here, and we ask him how much time there is between 2 points as seen by him. That gives some amount of duration, dt. You can also take somebody, and the ball's still there. Let him measure the duration at this point. You might get another dt. In fact, as you can already see from the equation, because it's r dependent, you will get another dt. Okay? So this guy and this guy will measure different durations between 2 points. Here's another example. Here's a guy who is walking through the space-time, and he is measuring the amount of time. That gives you another dt still. Now, you can think of all kinds of examples. You take somebody who's orbiting the thing. He will measure particular dt. Take somebody who's doing jumping jacks through the space-time. He will measure different dt still. Now, which of all the infinitely many dt's that you could have, which of these ones is the one that you actually see in the dt over there? Now that's a question that we need to find the answer to.
Isn't it like whoever is measuring? That was the whole point of general relativity.
Sorry?
Isn't it like whoever is measuring the...
Yes, but you will get different numbers.
Yeah, but then I thought you all were like correct.
Oh, no, you're allowed to use the formulas from all locations and with all velocities and these sorts of things. But you will still get different answers from one observer to the next, even though you're allowed to use the same formulas. Right? Do not make the mistake of thinking that general relativity or relativity in general means that everybody will measure the same numbers. That is certainly not true. You already saw that it's special relativity. No, relativity tells you that everybody is allowed to use the same formulas. But the numbers could surely differ from observer to observer. So this is a step that we have not encountered yet before because we simply have not really looked at a real curved space-time yet. So this is the first time we will encounter this. At the moment that somebody gives you a metric tensor and you want to go and calculate these sorts of things, you have to identify for yourself who it is, of all the possible observers, who it is that measures these particular durations and distances. So do you see that there's a question there? At the moment that you have not specified this for yourself, and you would solve this equation, right? You write down your Christoffel symbols, you have your 4 equations, you maybe solve it, maybe you find a full perfect solution. The solution does not mean anything if you have no idea whose time and whose duration and whose distance it is you are measuring. So, as a general rule, at the moment that you go into the general relativity, somebody gives you a metric space or a metric tensor, you have to first find out which observer is doing the measuring in these coordinates. Now, how to do that? That's what we're going to do now. Let's write down the line element for this thing. As you know, the line element looks like this. Somebody fill in some details? Can maybe somebody dictate maybe for me what I should be writing down right now?
Minus. Oh, plus actually. Wait, why 1? I thought open bracket 1 minus 2m over r dt squared.
Dt squared.
Yep.
You have no difficulty doing this, right? It's just writing out the line and doing the double contraction. Taking r squared minus.
We switch signs though.
There is an overall minus.
Because there's an overall minus here. Yes.
The first bracket.
There should not be a square here for some. I don't know why I wrote that down. So, was that the thing?
Yeah.
Okay. So if I write down the line element, I get something like this. Okay. Now, from a physics perspective, do you remember what d tau is? What it means physically? That's proper time. So, can you give a little bit more than just the name of the object? What does it mean physically? What does it entail?
When you have like 2 events,
Yes.
then the proper time is going to be the time for the person which didn't move like in the surface, right?
Yes, who sees the 2 events happen at the same location? That's the one. Okay. So, that will help us. This is always true. This is always the amount of time that goes on between 2 events that for one observer happen at the same location. That's what proper time means. But that teaches us something here. My question here is, what does dt mean? Whose time is that? Any idea how to get that out? If you know what left-hand side means, is there any way that you can find for yourself then what dt must mean?
You just use Lorentz. No, you can't. Well, could you just use the Lorentz transform?
No, we're not in special relativity anymore.
True.
Is dt the time for an observer who would measure r
distance between the two events? As in that
How do you
data.
figure?
That's what I was thinking too, but I don't think.
Because then all the coordinates would be related to one another.
So let me see if I understand correctly. You say you think that this dt is the amount of time between two events that are dr away from each other, for the observer that sees them dr away from each other? So
Yeah, that would be one case.
can you quantify that using this expression or not?
As an expression.
Yeah, well, there's an expression there. So it should follow from that equation.
I mean, everything next to the dt squared goes on the left-hand side, and you divide it by the 1 minus 2m there.
And so, okay.
So
I
that's
understand
the-
the steps, but
So that's the dt. But I mean, the person who sees like the event happening r distance away and a certain mass of m, with that specific relation is the one who's measuring it.
oh, you know what? I see something there. Let's take an observer who sees two events happening while the observer himself is not moving in this space-time. He himself is stationary. Okay? What does it tell you about the r?
0.
Is 0.
Gideon, can we repeat this part?
Yes.
What did the
Let's take an observer who himself is not moving in the space-time.
but
Who's-
moving? Who decides? If
With
it's
respect to
moving?
the m in the middle, right? We have, in this space-time, we have at least one point that is completely bolted.
So it's the center of the sphere.
This is, well, who is not moving with respect to the center of the sphere.
Ah, okay. So we have a. Okay, okay.
Okay, so what does it say about the dr for that observer? That is 0. Okay, so I'm going to take this equation, I'm going to apply it to a very particular observer. I'm going to take the observer who himself is not moving with respect to that big mass in the middle. So that means that this is 0. If he's also not moving, so he's at a fixed radial distance from the big ball in the middle. He's not moving inward or outward. Okay. Secondly, suppose that the guy is also not moving along one of the angles. He's not circling the thing that we're looking at. What does it tell you about the d thetas and d phis? Sorry?
0.
Those, both of them are then 0. All right, so if we're going to take an observer, you know, all these 50 million observers that we think about in this curved space-time, we're going to focus on one that happens to be stationary with respect to the big ball in the middle. He's not moving inward or outward. The r0 is not moving in some circular orbits around it, so d theta and d phi are also 0. Then for that particular observer, you will find that d tau squared equals 1 minus 2m of r dt squared. Well, that cleans up stuff, yes? We were looking what dt means. All right. So we've gotten rid of all the other variables, and we're getting very close to just having dt equals something, something, something. Let's suppose we take that observer, the one who is stationary, who's not moving, who is also infinitely far away. Yes?
Just a question, if you were in
Yes.
Minkowski space-time, then that equation would just yield d tau squared equals dt squared,
Yes.
which isn't true, is it?
Yes, it is. For an observer who sees two things happen at the same location, that's absolutely true. That's exactly what proper time means.
Sure. Okay.
And by the way, we're getting to the same conclusion here.
Yeah.
Because we already specified that this particular observer is not moving, so it's a stationary observer, stationary with respect to what? The mass in the middle. And let's, in addition, say that it's infinitely far away from that mass in the middle. So that means he's not just at a fixed r, he's at an infinitely far away fixed r. So this part, it just tells you stationary observer. Now let's take the guy infinitely far away. Tell me what happens. This becomes 1. So this is stationary observer plus infinitely far away. take a square root, left and right. You get dt equals dt, d tau equals dt. Yes. That's clear enough. Now, mathematical purists will come along and say, well, it could also be minus dt. Yes, that's true. That means that two observers have their time moving in different directions. Okay, well, let's stay within physics and say that whatever these two observers are, both see the time move in the same direction. Right? You will get this. This then tells you what dt means. Remember, the question was, you have many observers that you can point out in this curved space-time. And the question was, well, whose time is being measured by the dt here? Can you read off the answer now?
Someone who is infinitely far away and not.
Exactly. Exactly.
Does
What?
that apply to all the coordinates?
Yeah, well, that is the second step, yes. We've shown it now for dt. We have now seen that the dt, apparently, of all the possible durations of people that could have been in this space-time, of all the ones that could have measured the amount of time, this amount of time corresponds to the amount of time measured by a person who's infinitely far away from the thing in the middle, and himself is not moving with respect to the thing in the middle. That is that guy's dt.
What would happen if you would have space-time where that never happens? That it's basically flat, like if you weren't spherical space-time, for example.
I have to parse your question for a second. When you say if that would never happen, what do you mean?
Like space-time is equally curved everywhere.
Yes. It is here, by the way. This is equally curved, right? Oh, you mean equally curved even at radial distances? That is a good question. If you have a space-time that is spherically equally curved, just like this one is, and on top of that, the amount of curvature at any distance from the center is also the same. Can you think of a space-time that is not just curved in every angle, but also in every distance? We have the same amount of curvature everywhere.
Would not be exponential.
Why would it be exponential?
No, it would not. It's just a sphere.
Well, a sphere has different curvature.
Ah, that's true.
Maybe if I make my sphere bigger, then my curvature becomes less. Good question. Let's not dwell too much on this. One particular example of a curved space-time that doesn't just look the same at every angle, but also at every distance from some center would be, again, Minkowski space-time. Yes. So that's sort of a boring space-time. Is that the only one? No, there's more of them. And there's a whole series of metric transfers that are space-times that are not just the same at any angular distance in space, any angular position, but also any radial distance. And there's more than just Minkowski space-time.
Okay.
But this is all that I will say about this for now. But I would say this, expanding space-times that become bigger in time. Yeah, that will give you expansion of the universe and these sorts of things. Okay. So, the key message here is, again, if you're going to do general relativity and somebody hands you a metric, even if you know how these coordinates are called, you still have to do some work to find out whose coordinates they are. Now in this particular case, we find that this amount of distance, that infinitely far away from the center without moving yourself, that amount of time is represented by this number. That's what that number means. Any other person, so a person who is not infinitely far away or is actually moved through space-time, will also measure a certain amount of time. It will not be given by this number. Okay? Question to you. If I were to ask, well, let's look at somebody's duration, but that person is not stationary and at infinity, how would you calculate that guy's amount of time? How would you do that? So if somebody is moving through space-time, here's the big ball in the middle again. Here's the guy infinitely far away, not moving. He measures dt. Fine. I introduce a second observer now. That's me, who's happily moving through the space-time. And my amount of time I would like to know. And look, I am not stationary and I'm not at infinity. How would you calculate my amount of time? How would you do that?
Wouldn't you use the same formula because d tau is invariant?
Yes, there you go. Thank you very much. That's exactly what I'm looking for. Do you remember the details in invariant? Yes? So if you know some person's detail, so this number is fixed, and they introduce this other guy, that was me walking about, you get some other guy's dt, agreed? Okay, you can relate them to each other now, because you know one guy's detail. You have to look for some other guy's dt. Of course, you do have to put in how the guy is moving through the space-time. That's not very hard, because how he's moving through the space-time is represented by the way that his thetas change through time. So you can relate these numbers to each other. Now, for this reason, that if you have somebody's amount of time that you know what the number is, in our case, the infinitely far away guy, you can relate it to any other person's time, no matter how that person is moving or being located at a particular position in space. You can always calculate that stuff by referring back to that one guy that you do know. So it's very important that you understand who that person is, so you can relate all other observers back to the other guy. For that reason, this guy in this context is called the bookkeeping observer. It's the guy with respect to whose time you're measuring everything. And here comes the idea of relativity again. The best of relativity can tell you is how much duration there was for one observer compared to the other guy. So you always need to know at least one observer of whom you know the amount of time between two events. Now, in this case, again, it was simple. We found this is the stationary guy in infinity, that's the bookkeeper guy, and all other durations you can measure with respect to that guy. And then you can relate them to each other. That's the idea. All clear in our methodology? All right. Then I propose that we have a break, and then let's apply it. Let's actually introduce another observer and see how that guy's time and this guy's time are related to each other. Yeah. By the way, for the people interested, there is this particular book on black holes. It explains general relativity starting from principle nothing. It just says supposing you only know Newtonian physics and you only care about that part of general relativity that deals with black holes. There's this one book that is called Black Holes, Introduction to General Relativity. So if you're looking for any other curved space-time, you will not find it in this book. It's a complete book only on black holes, and it is by Taylor and Wheeler, and the Wheeler is this Wheeler. In fact, Wheeler, John Arnold Wheeler is
another 45 euros.
I don't know, you know, it's more expensive, this book. Unfortunately. Yeah, I know, it's terrible. What?
How much?
I don't know, it's 80 euros or something like that. I believe something like that.
What?
Yes, but it's my understanding you guys are very good at Googling yourself through free copies of books, so I'm sure you can find a copy.
The hard copies.
Well, I love hard copies. I don't understand what people use PDFs.
Yeah,
I mean, there are little trophies that you have in your bookshelf. I mean, this is what I conquer.
You can stay free.
Just in case.
I gladly did not leave for 2 weeks so I could buy a book on black holes. Yeah, absolutely. Please go ahead. So it's a fun book. It's very physics first, so yes, it does all the calculations, but it does explain everything just in terms of physics. So there's very little line elements in there and metric tensors. It just says, well, apparently it works like this, blah, blah, blah. One final comment on Wheeler, John Arnold Wheeler, is that he is actually the guy who came up with the name black hole. Because if you look at this expression, there's nothing in there at first sight that tells you that things cannot send out light or anything like that, right? And Einstein himself did not believe that this was actually a solution. I mean, he was mathematically convinced that yes, this was a solution, but he said, no, there's something wrong with this solution. It doesn't feel right to me. One of the conclusions, one of them we're going to reach during the tutorials, is that indeed you could have locations in space-time where light is being absorbed and never comes out again. That is all written in this space-time metric. Just give me a second. Then Einstein thought, well, that's probably just nonsense. Okay? How can you have a location in space and time where things are so curved inward that even light cannot escape anymore? So Einstein discarded this solution as just a mathematical oddity. Yes, the solution exists, but it's not what nature does. And then Wheeler took this very seriously, and he worked on this. And then he found ultimately that yes, these things exist, and he found with many other people, of course, but he found, well, these things do exist, and do have space where light does not come out anymore, and then it was Wheeler who said, let's call this thing a black hole. It was in the 1940s or so. So, hilarious book.
No, it's just nice how you answer your own question in the comments later on.
Yeah, that's another thing that I like about actual physical books, that you can write your own little notes, and 15 years later, yeah, everybody's going to read my student notes now, yeah, in the book. Feel free, go ahead. Can I just check for a second what it is that I wrote? Question, is it time and distance measure take into account the motion that light has? Now, well, look at that. Rodrigo, here's your question. Sorry, just
including
completely unscripted this, but Felix was just pointing out that I wrote a question in a margin here, namely when the effects that we're looking at in the remaining of this chapter had anything to do with light travel time, the fact that you might be seeing things over there, but the light first has to arrive at you before you actually observe them. The answer is no. All the effects we're going to derive have nothing to do with light travel time. Yes, if you're going to measure in real life, yes, then you have some travel time to take into account. But in practice, as in your calculations that you do, that effect is left out. And Rodrigo was actually asking me this during the break, and apparently I was asking myself this when I was studying this book, and there you go. So do I write an answer as well?
Yeah, you do.
Okay, good. Is it the correct answer?
No, TNS are uncoupled from the travel time something to observer. To put A in, I can't really read it. But
Okay, well, I hope my handwriting has improved in the last 15 years or so. Sorry, yes. No, there were two questions. Ali.
Yeah. So this symmetry tensor is only for black holes, not for the spherical mass?
No.
It's for
It's for any spherical mass. When we discussed why of the many possible solutions that you could have had for a zero right-hand side of this, I said this one applies for a spherically symmetric mass distribution. Now, I very quickly then just used the word black hole, but it applies to all spherically symmetric mass distributions. In fact, the curvature of space-time around the Earth is also given by this one. If you take into account, if you assume that Earth is exactly spherical, and if you assume that the amount of mass in the Earth itself is homogeneously distributed, which it isn't. But by good approximation, this holds. In fact, there's a very important theorem, mathematical theorem in general relativity that says if you have a spherically symmetric mass distribution, then there's exactly one metric tensor that describes it. And
So
that's this one.
the relationship is an if and only if between the Schwarzschild metric tensor and the isotropic spacetime?
Yes.
Okay. And in the
in vacuum, I should say.
Yeah. And
Sure.
in the isotropic spacetime, we also include the Minkowski.
Yes.
Okay.
So there's exactly one solution. This mathematical theorem is called Birkhoff's theorem, if you care to look it up. Ali, just one more. Yes, go ahead.
The physical properties of black holes, like the fact that light can't escape, can
Yes.
those be directly derived just from the tensor,
Mhm.
or did we need observation?
No, that comes all from here. Now, we're going to see this during the tutorial, but it's sort of like an open discussion right now, yeah. But let me already try to take away one misconception that people might have about black holes. So, the correct answer to your question is, I use black hole here, but I should say spherically symmetric mass distribution, including the Earth, including the Sun, including whatever, as long as it's spherically symmetric and it has mass, and you look at it from a vacuum, then this is the solution, and Birkhoff's theorem tells you this is the only solution. So you don't have to look for that maybe some other star might have some other curvature around it. As long as it's spherically symmetric, this is it. Now, and what was your second question?
The physical properties of a black hole.
Oh yes, yeah. That's the misconception that I want to take away. It's good to hear it now. Sometimes when people think about black holes, they think about it in very Newtonian terms of the word. That they say, well, a black hole is this object, has a lot of gravity. So far true. And light tries to get out, but the gravity starts pulling it back, and therefore light never comes out. Now, what is wrong with that argument?
Circles around.
That it stays into a circle? That is true. There's
Well,
something, it's called a photosphere, that's true. That's not what I mean though. What is wrong with the argument that light tries to get out, but the gravity is so strong that it's being sucked back in? What goes wrong there?
It has to stop at one point.
It has to stop at one point, or has to. I mean, even before it stops, it has to slow down. Light does not slow down; it always goes with the speed of light. So this argument simply does not hold. So the idea that it's sort of like a ball that you throw up, but it's being pulled back by gravity, is simply not true. This is literally sometimes that you see in books, not in general relativity, but sometimes like Newtonian physics, that it really says, well, it's like throwing something up, and you can calculate how fast you have to throw it up in order for it never to be able to come down again, right? It's escape velocity. If you take the escape velocity to be the speed of light, you cannot throw it any faster. And then you would calculate how big that mass should be. You actually do get what we call a horizon of the black hole. So if you use this faulty logic in Newtonian physics, you actually do end up with the right answer. But the logic is faulty. Now, just out of curiosity, can somebody guess if it's not the acceleration of light that makes black holes black, what it is then?
The curvature of space-time.
How? Yes, that's
Like
correct.
it's so
How?
big that light cannot like leave the curvature.
But something happens to the light,
Right.
yes, as it moves through the space-time.
I was saying like it circles, but I'm just not, you have the black hole, the light just keeps spinning around and it
Okay.
gets closer and sort of folds in, but I mean it just
Okay.
circles around it.
Well, that effect certainly exists. It's called the photosphere. And that circle exists at a radius of 3 times the mass of the black hole. Sure.
But
That-
not necessarily that it stays like it spirals inwards. That's
Oh,
what I mean.
oh,
Like
that's-
it gets
okay.
sucked in, it spirals really quickly, but it just goes further inwards, and that's how it goes.
I understand the argument, and so you can make that situation happen. But what if I take a photon gun laser and I shoot it radially upward? There's no angular motion to begin with. How would it then end up in this circular motion if I never gave it that initial velocity to begin with?
What do you mean by radially off?
Do
That's,
you mean from inside the black hole, or?
Yes, suppose that I stand somewhere in the middle of the black hole, somewhere in the middle of the space-time. Let's forget about the fact that you die and everything. You just stand there and you send a photon upwards, yes? Now your argument is, well, a photon can get trapped in some sort of circular orbit, might spiral in or something like that. That is certainly true. That effect actually exists. But then the original photon should already start in a circular motion. Somebody should have shot the photon with this little hand light in already a circular motion to begin with.
Doesn't that always happen?
No, I mean, in principle, I can think of a situation where I stand somewhere close to the center, forget about me dying and everything, and sending out a photon radially.
Okay, if you send it out from the center.
Yes.
that's true.
Then there's absolutely no way that all of a sudden it gets trapped into a circular orbit. So your effect exists, but it's not the reason why a black hole is black. Any other suggestions? It's a very unscripted lecture today, but it's very fine. It's good.
The time stretches out indefinitely, so the
Okay.
speed of light doesn't really matter because, well,
Well,
the
speed of
proper
light, so
time's
the-
zero,
the-
like the proper time's infinitely long.
Yes, but it already was, right? Because the photon already had.
That's true.
Yes, there already was, even in the Minkowski space-time, there was already infinitely time stretching. So that is not an effect that, or the effect happens, but you won't register it because it was already infinitely stretched. But yes, I mean, maybe then it does have something to do with some sort of time dilation, maybe.
I mean, even for the observer,
Mm.
said no speed
From
time is
outside.
dilated, so even if
Yes.
there are no
Yes, it
speed
is.
observer, the light isn't going to travel anywhere because it's dilated too much.
Okay, so you're saying that if you get close to a black hole, aside from dilation that you might have because of your special relativistic motion, the fact that
Yeah.
you move, there's also some dilation that has to do with the curvature of space-time itself. In fact, it has to do with this, right? Because this is what goes with dt. So yes, something does happen there. In fact, can you see when it happens? When does this become
Zero.
sizably different?
When the mass is very big.
Sorry?
When the mass is very
The mass
big.
to radius.
Or when you get closer to the mass.
Okay, but
The
do you,
radius is 2 times the mass.
yes, I mean, you're saying the same thing, but I was very specifically looking for a particular position away from your black hole. If R is 2m, then this becomes 0. Agreed? Okay, that means something. Because that means that in your line element, all of a sudden, this gets multiplied by 0 at that position in space. That means that time becomes extremely dilated due to gravity alone. Now, there's many ways that you can physically try to interpret that, but one way of looking at it is, well, if you take your light to be some oscillation, and there's a particular frequency, how many times per second it oscillates up and down, then at this particular distance, r equals 2m, apparently the oscillation has gone to a standstill. It doesn't oscillate anymore.
It's still gravitational redshift.
That is gravitational redshift, yes. That means that apparently that the closer you get to a black hole, or in other words, the more you make this close to zero, the oscillation of your light becomes slower and slower and slower. Not its speed is still c, yes? Not how fast it's doing like this, but how fast it's doing this. That slows down. And if you literally make it zero,
Is that the frequency?
that's the frequency, yes. Now if you make a light with frequency 0, put it in energy. What's the energy of light?
H times its frequency.
Yes, that's h bar times its frequency, yes. But now you make the frequency 0 because of this effect. How much energy is there still in the light?
0.
0. So there is, if you want, there is still light moving out with the speed of light. It's just that its energy and its frequency is 0.
So you don't see it.
So you can't see it. It's infinitely redshifted. So that's what happens. So this is why a black hole is black. You actually call it a red hole, right? I mean, the closer you get to it, the more red your light becomes because the frequency goes down, down, down. It becomes infinitely red. And apparently infinitely red in this context means black. Yes?
It might be a bit too far, but how can Hawking radiation then get out?
Oh, now that is a completely different story. There's always somebody who wants to drag quantum mechanics in, okay? Okay.
So it's okay.
No, that's fine. The short version, yes? Short version is that the gravitational field itself comes with energy. Yes?
In the sense of quantum field theory that you have.
You don't even need well, ultimately you will need quantum field theory, but the idea is that the gravitational field itself has energy. And the more energy empty space has, the more easy it is to make a particle-antiparticle pair. Okay, but that means if you make that pair, you've stolen a little bit of energy from your gravitational field, agreed? And you have now two particles. Now usually in normal quantum mechanics, Jaco's world and everything, these two will annihilate within a time delta t, and delta E times delta t is h bar over 2 or something like that, right? Heisenberg for energy and time. But if you're close to a black hole, and it so happens that you pull two particles out of your gravitational field, you steal a little bit of its energy, and it just so happens that one of these particles is unfortunate enough to be below this r, where it gets sucked in, and the other one is not. Then you have one particle flying out, one particle falls back in, but you have taken away energy from your black hole. And that particle that flies out, that is your Hawking radiation, and now you understand that the energy that that particle takes away is how much you have stolen energy from your black hole. If you keep it up long enough, you won't have any black holes left. That's the shortest version. All right.
Unrelated to this, but one question you're saying this works with any spherically symmetric object?
That's Berkeley's theorem, yes.
But wouldn't this only work for a point mass? Because, for example, if, in Earth, where mass is equally distributed,
Yes.
If you would, for example, go inside of Earth,
Yes.
well, then that doesn't hold anymore.
Actually, this Berkeley's theorem that I said, that the curvature of space-time looks the same regardless of the spherical mass distribution. Yes. That is also true in Newtonian physics. Even if you don't have curved space-time, if you just look at the gravitational field, there's an exercise that actually Newton himself already did in his famous book from 1687, is that he calculated that it doesn't matter how you distribute mass spherically. You can all put it into one point, or you can smear it out over a big ball, or maybe take it all in a shell. It will still give you the same gravitational fields from the outside. So if I were to take the Earth and I would squeeze everything together, but I do it spherically, and I make the Earth a radius 2 times as small, the gravitational field, your Newton's law, would still be exactly the same. In fact, you can already tell, because Newton's law just cares about the amount of mass in its totality, right? You have to put the mass of the Earth in and not its shape, or how that mass is distributed.
Once it's inside of Earth,
No, then it changes. I agree.
okay, so this only goes outside of the...
Yes.
Okay, all right,
Yes.
yeah, no, that makes sense.
Okay. So just to make a point that this idea that curvature in our what we call gravity in this context looks the same regardless how you spherically smeared out your mass. That was already true in Newton's gravity. It just happens to be the same still in general relativity. Now, yes, sure. I mean, we have an open question session anyway, but I will do this calculation in all.
It's gonna be quick.
Sure, go ahead.
Regarding the units.
Yes. Yeah. Yes. See question 1B of the tutorial, but go ahead. There's units missing.
Then we can talk about it in the tutorial.
Okay. I didn't want to bump your question, but it is actually a question of that we're going to discuss during the tutorial, because yeah, I mean, it seems the unit is missing, right? This is unitless, and I have a kilogram over meter. Now, kilogram over meter. How can you subtract that from the number 1? The answer, of course, is this is not the answer of 1B. There's still work to be done there. That is that these numbers are both put to unity. So a question that you have to ask yourself is, well, apparently there's units missing, so there's G's and C's missing. How do you have to put the G's and C's back in? This is actually exercise. G times over C squared. That makes the units come out okay. You haven't seen this, okay? You will do this yourself during the tutorial. Now, let's do a calculation. For demonstration purposes, I think the easiest exercise for now to do, mathematically speaking, is to introduce one observer that happens to be happily, well, should we do a rotating one, or should we have one that is standing still outside the black hole, just not at infinity? Both of them work, both of them are mathematically easy to do. Any preference? So we have our observer at infinity, the bookkeeper guy. I'm going to introduce some other observer, we're going to compare their times to each other. Okay? Who's the other guy? Are we going to take a guy who's circling the black hole or the Earth with the spherically symmetric mass distribution, or are we going to have a guy who's still stationary but just not at infinity?
Stationary and not at infinity.
Stationary, you can sort of feel this is probably easier, okay? Okay. You know what? For that reason alone, I'm going to take the guy who's, I should have asked. I mean, I'm going to do this one. Let's do that. So I'm going to take 2 observers. One of them infinitely far away, stationary, and the other guy is going to be orbiting the black hole. By the way, I keep on saying black hole, but whenever I say black hole, also people at home watching this in India, I mean spherically symmetric mass distribution. Okay? It's just in my context, it's always black hole, so this is why I keep using the word black hole. So we're going to have 2 observers, 2 people. Here's your black hole. There's this guy all the way at infinity. Let's give the guy a name. Let's call that person A. Now we're going to introduce another guy who is orbiting the black hole. And let's call that person B. I'm going to write him in blue. We're going to relate the amount of time that passes for this guy, the bookkeeper guy, and guy B, the orbiting guy. We're going to relate these 2 numbers to each other. Relativity cannot tell you how much time passes for one person. You have to compare people, okay? Now, we should have little difficulty doing this. What we're going to do is the following. We're going to write down the amount of time that passes as seen by the infinity guy and as seen by the B guy, the orbiting guy. Let's start, that's what I'm going to do in black, the infinity guy. Here's our Schwarzschild line element. This is the r squared minus r squared d theta squared minus r squared sine squared phi d. This is the line element again. Now, one more time. How much is this guy changing location? Yes, Natalie.
I think your last term is sine squared d theta. And then d.
Oh, you're right. Thank you. There you go. That's the phi. Yeah, that's the one that you meant. Sure. So.
And also the
guy
sine.
defense-
The same.
Sorry.
Sine squared theta.
Oh, jeez. This is okay. double mistake there. Okay, there we go. Good, thank you. It won't matter anyway because they're going to be 0. So you have a guy at position A not moving about.
Yeah.
Okay. We saw that before, right? It's the exact same exercise. Not orbiting himself means that these are 0. And also means because he's radially standing still, that one is 0. And because he's infinitely far away, this particular r itself goes to infinity. 2m of r goes to 0. So we get d tau equals dt. Okay, no surprise there. We concluded that before. That was what the dt meant in our line element. Right? That was the first exercise that you do when you are given a metric tensor. Find out whose coordinates you are looking at in the metric tensor. Now, so this is all fine. Let's do the same exercise now, but for the orbiting guy, so that's in blue. I'm going to write down the same line element. One minus 2m over r minus 1 dr squared minus r squared. Okay, now you tell me, this guy.
Yeah.
I'm hoping for more contributions to say.
Is the orbiting just in the phi or the theta plane, or some combination?
Yeah, let's be more specific. Let's say that it's orbiting in the phi direction. So if the ball's over here, this is our z-axis, and as you know, theta is measured with compared to the z-axis. So that one is fixed. So let's take this floor here as being the plane in which he orbits. So what does it tell you about theta?
Orbits at a constant.
Theta is not 0.
Yeah.
D theta 0.
D theta 0.
But
And
theta is by
itself-
half.
Constant, so 0.
Yes,
Because,
yes, and that constant is pi over 2, yes?
So sine is 1.
Okay, so that means that this is 0, and this sign happens to be 1. Good. So, this equality sign means fixed theta plane, and not just a fixed theta plane, but pi over 2 plane. You don't have to, by the way. I mean, feel free to take however the guy is moving about. In our example, we're going to take him being at this fixed plane. So it's a fixed theta plane, and which plane is that? It's the pi over 2 plane. Gives me this. Minus 1 over 2m r dr squared. Minus,
That for this one.
Yeah.
is it? For what reason?
I mean, if he's just spiraling down, if he's constant orbit,
Yes.
then R is 0.
But
Oh, it's constant.
this is why I say there's many solutions here, but let's, for the sake of demonstration, let's take that he's at a constant r. So this guy is not moving inward or outward, no spiraling. So yeah, that means that this guy, this term is also 0 because of this one, yeah. So in this equality sign, there's another assumption, and that is that r is constant. And you know what? Let's give it a number. Let's call it radius a. Some number, just not infinity. All right. Then what I have left still is r squared. This sine squared theta is unity. I get d phi squared here. Oh, and by the way, now that this guy's r has been fixed to capital RA, still with me? Just taking the line element, putting in this orbit. Anything else we can do? Do we know something about d phi maybe? You know what? Let me, for fancy's sake,
Well, it has to be a certain value.
does it for a reason?
Otherwise, the guy would start spiraling inwards. If the two forces do not cancel each other out, the guy would have.
Forces. What force are you talking about?
I mean,
The gravitational.
yeah, exactly. I'm talking about from a Newtonian perspective.
Ah,
Yeah,
but,
which is not the
but
best
maybe we
idea.
shouldn't.
Yeah.
It's relativity now, okay?
But it has to cancel in that sense, the curvature. Like,
Okay, Okay, so the curvature, that's the force being pulled in.
Yeah.
Let's talk Newtonian for a second.
Yeah.
The inward gravitational force and the outward, what is the outward one?
It's the centrifugal.
Okay, but centrifugal, we saw 2 lectures ago, is really just a fictitious force, yes?
Indeed.
But we also, the fictitious force is already taken into account by the Christoffel symbol. Because we went to fictitious forces you get when you go to a non-inertial system. So you don't have to, by hand, put in this centrifugal force, it's already in there. That's how we got to this formalism in the first place. By the way, what I did here, I took a dt out, yes? It's the same expression still, but I do this for a reason, because what does this mean? d phi over dt.
It's the angular velocity.
Yeah.
That's the angular velocity, how fast this guy is moving in this direction. Typically you call it omega. How fast is the guy moving? So this thing here, just by definition, is omega. Agreed? We have to be careful here. An omega means how many angle per second. Now whose second is that?
For the guy that's spiraling,
Why would that be?
because what's the thing we're trying to find now, right?
I agree, but I subject to you
Yeah, but
that
we've seen what dt is.
Yeah, it's the same guy that has the DT,
Yeah.
so it's person A.
Yeah.
there
exactly.
we go. Look, this dt we have already identified is the amount of time as seen by the guy at infinity, who is himself stationary. So what we see here is that this angular velocity with which person B is moving about is the angular velocity not measured by the guy himself, but by the guy at infinity. If you ask the guy at infinity how fast is person B moving about, then person at infinity, he will give you his omega. If you're going to ask this guy himself, he will also come with an omega, but with a different omega. Why? Because his time is different.
One question.
Yes.
Then is d tau that we're looking for now the time of B?
Yes.
Okay, okay.
Because this d tau, we're almost to it by the end of this calculation, by the way, but d tau, if you recall, is the amount of time that passes for a person who sees 2 things happen at the same location. Now, if you are person B moving through your orbit, yes, and 2 events are you are here in the orbit and you're a little bit further away in the orbit. Now, then you yourself are the person seeing those 2 things happen at the same location, right?
Okay.
It is your coordinate system, so you, d tau here, is the coordinate of the guy who sees things happen at the same location. Now, certainly person A will not see person B be at the same location at any moment in time. Person B will see himself at the same location in time, namely at his origin of his coordinate system. So what I'm pointing you towards here is, this d tau is not that d tau.
Definitely.
This d tau is the amount of time as measured by the guy who sees 2 events, the 2 events being at one point in its orbit and the next point, at the same location. So let's actually give that a little name. Oh, by the way, I have no idea why I call this RA, it should be RB. It's the radius of where the B person is. Sorry about that. Do you all see this point? That the d tau that we're calculating in blue now is the amount of time that passes for the guy who is orbiting. You have to really understand that why that is true. Yes?
So the question is, since A is infinitely far away from the mass distribution, any distance seen there is exactly in the same point. I mean, if you're infinitely far away from something, any distance in the limit will go to be the same, right?
Not sure I follow. So if you're very far away,
So if you make 2 points on that whiteboard and you move infinitely far away,
Sure.
they look
Yeah,
to be
yeah.
the same. In the limit, the distance becomes the same.
I agree, yes.
So in that sense, the d tau of A, I mean, A sees the 2 events happen at the same location as well, because he's infinitely far away. In the limit, I mean.
Yes, but it's in the limit.
Yeah.
So and that makes a difference.
Yeah, but we're considering him to be infinitely far away, which is itself a limit.
I
in a sense.
agree. So it feels like that's...
No, I mean, it's just.
Yeah, no, but that's a good point. For people who are not following, his question is subtle. He says, but wait a minute. 2 positions within this orbit, take these 2 as the events. 1 position in the orbit and the next position in the orbit. For person A, in the picture you would say, well, person A doesn't see them happen at the same location, right? But then Simon makes a point, but wait a minute, if you're really, really, really far away, then it's going to be very hard for you to see that the guy has moved at all. So in a particular mathematical way, the fact that person A is very infinitely far away makes him look as if these points are far away. But here's a key difference. So the question is extremely valid. Okay? Here's the reason why I'm still going to do this as I do it. And that is that this guy, this person actually has moved. Yes? If this guy, person A, would have extended some huge, infinitely long measuring rod, and the measuring rod lights up at the moment that person B travels by, he would actually see that they would have happened at the same location. So the confused, do we all see this? That even though it looks from an infinitely this far away as if this is hardly any motion at all, and therefore also happens at the same location, it's not actually at the same location. This guy has a measuring rod, extends all the way, there's a little firecracker on both positions, and bang, bang, he could actually tell that they are a particular distance away from each other. So there is really a distance, even far away. Now, compared to this, you and Rodrigo are sitting a particular distance away from each other. If I move very far away, that distance is going to look extremely small. If I'm very far away, the two of you are exactly the same point. Yet, if I would throw out my measuring rod, I would actually be able to tell that you are still away from each other. So, the key lesson here is, do not confuse what this person actually sees by sight by what is actually true in his coordinate system. Those are two different statements.
Yeah, you
Yes?
can make a sort of local measurement.
Yes,
That's
you
it,
can.
yeah.
Yes, even if the guy's here, it's impractical for him to make the local measurement. In his coordinate system, locally, there is a difference between the 2 points. So, if you recall, there was a similar issue in special relativity. That in special relativity, you could also have that two events happened somewhere in the distance, right? And then you could ask yourself the question, are these two things happening simultaneously? And you might then think, you know what? If something happens over there, exploding firecracker, and some other firecracker happens a second later, but the second late firecracker happens to be a little bit closer to you, then the sounds of these two firecrackers will probably arrive at your ears at the same time, and you might be tempted to conclude the firecrackers exploded at the same time. They didn't. If you would have been there locally, you would have actually seen, if you would take away the travel time of the sound in my example, you would have seen that they are actually at different moments in time that these two events happened. Very much something similar is happening here. Does that make sense to everybody? Do not mistake a local measurement from what you would optically see from a large distance. Now, we are here at this point, yes?
Could you maybe write the omega as an omega of tau?
What if I put omega A? It's the
yes.
omega as measured by person A. Would that work?
Yeah, sure. That's
Good.
great.
Okay. That's a good question, right? I mean, you see an omega, so you think, oh, it's an angular velocity. Yes, but it's measured in the infinitely far away guy's time. Good. By the way, we're done. Because let me write down my d tau b here. The amount of time that goes on for this guy, for him to travel from here to there, is apparently given by the expression that I'm now writing down. So one more time. The amount of time that has passed for person B to go from here to here, as seen by himself, is given by this expression. If you would literally ask him, how long did it take you to go from that point to the other point in your orbit, he will say this amount of seconds. Yet, if you would ask the bookkeeper guy, the guy at infinity who's viewing it from a large distance, he would say, no, the amount of time was this.
One question, is the dt outside of the square root sign?
Yes.
So it's not squared?
No. There used to be a square. There used to be a square here. And then in my continuous sloppiness, I forget putting squares and everything. Okay. This, by the way, is why PowerPoint would be good. You would not have this issue. Now, we have this guy's amount of time and that guy's amount of time. Let's relate them to each other. Let's see how much time there is as seen by one guy compared to how much the other guy is seen. It's a very simple step. Who can make it?
Just replace the t with the tau.
Yeah, that's exactly what we did, right? We already concluded that dt that appears in the line element is actually the time is measured by the guy at infinitely far away. So I might as well replace this guy's dt by the d tau that we have over there. So I'm just literally putting in this thing here. And you know what? To get the nomenclature, the notation right, we constantly kept calling this guy person A, so let's call d tau A, just to be sure. And now, let's write it down in one beautiful expression. The amount of time that passes as seen by one guy, compare the amount of time that passes as seen by the other guy, d tau B over d tau A, is apparently given by this huge square root over here. Here you go. Here's time dilation between those two observers. That's a beautiful looking expression, isn't it? We have a couple of minutes left in which we can do some fun interpretation of that formula.
I have a question.
Sure.
So every time we have d tau, so every time we have proper time,
Yes.
100% of the cases we are implicitly talking about the distance between two events in terms of proper time. So every time we have d tau, we also are talking about two events.
Yes.
Now, since d tau is invariant, and there we have two different d taus,
Yes.
it means that actually we have two different couples of events. But for d tau B, it's easy to see what events we're talking about. Can be, for example, B being in x1 and B being in x2.
Yes.
Those can be events that are taken into account by d tau B. But what are the events that are taken into account by d tau A?
Same set of events.
But we said that d tau is invariant, so for the same set of events, d tau should be the same.
What does invariant mean?
That it's the same. That it's the same for every observer. If you change if you have a different observer, then the observer will measure the same amount of proper time
in
between two
special
events.
relativity. The invariance has to do with you looking at two events and then seeing it from a moving system. That is invariant. We're now doing something else. We're looking at two events at a different location. There's a different statement.
What do you mean?
Usually when you, it's a good question. Do we all understand the question? Because if there's one thing that you have picked up during special relativity, electrodynamics, and also during maybe the first week or so of this course, is that proper times should be invariant, yes? Now invariant, and his question is an extremely good question, so thank you for it. It will elucidate things. His question now is, but wait a minute, we now have two different d taus, but we're looking at the same two events, so let me be clear about that. Both of these two d taus refer to the same two events, the two events being this guy being here and that guy being there. Same two events. And his question, extremely valid, especially after everything that he's seen this year throughout his physics courses, is I thought these numbers should be the same. There's invariance. His question is extremely valid. Here's the solution. Invariance means that the numbers look the same or are the same in if you would go to a different coordinate system. If you would move to some other guy's coordinate system, then it would look different. Or then it should be the same. Do you agree? Both of these two observers, though, in this particular example, are still in the same coordinate system. They're still using the same t, r, theta, phi coordinates. They have not shifted coordinate systems. Invariance is a statement about do numbers change if you go from one guy's coordinate system to the other guy's coordinate system. But we haven't changed coordinate systems here. The only thing that we've done, we've changed location.
By saying changing coordinate systems, would that be equivalent to going from unprime to prime?
Yes. Yes. We haven't gone to prime versus unprime systems. We're still in the same original system.
But don't like. Isn't it that two observers are staying in the same original system if they are at rest with respect to each other? But here we have A that is
Yes,
not at
that,
rest.
no,
with
that, no, no, that was an equivalent statement as long as you stick to special relativity. Or
Okay,
nothing
yeah,
more.
yeah. And how do you apply it to this
Well,
case?
how would you change the situation? If you would take the whole space-time and change the space-time itself by some other coordinate system, then the invariance question comes along. Then the details should be the same.
But then how can we have the same coordinate system if the two observers are not at rest with each other in
Yeah,
this
I
case?
don't-
Like how physically is
I
it
don't get
possible?
Do you agree with me that they still make use of the same coordinates? They still make use of the same t, the same r, the same theta, and the same phi?
Yeah.
Okay, that means that they're still in the same coordinate system. In special relativity, when we move coordinate system, we went from one guy's t to some other
another
guy's
guy's
t
t,
prime,
yeah.
and one guy's r to one other guy's r
Yeah,
prime,
that's true.
and one other guy's phi to one other guy's phi prime. That step we are not doing here. We're still measuring, both observers are still measuring their numbers in the same set of 4 units. There's no going from prime to unprime system or the other way around here.
Yeah, but my question is how can we ignore what special relativity told us about using different
We're
coordinate
not.
systems?
And let me, in fact, your question is good, but I can answer that by going through the last couple of steps of this exercise. Okay, now we put extra emphasis on this question, but just to be sure everybody understands the question and its answer. Invariance, you might have gotten to know as a statement that says, this number should really be the same from one observer to the next. The statement is more stringent than that. It says if you go from one guy's coordinate system to some other guy's coordinate system, you go from x, y, z, t to x prime, y prime, z prime, t prime, then the number should be the same. No such transformation has been made between these two observers. The only thing that we've done, we've described both observers still in the same coordinate system, it's just that they move different. That's a different statement. The invariance idea that the number should be the same does not apply in that case.
Then it also does apply here because when you were doing the final step, you said, okay, because of the invariance that we have here.
Yes.
Isn't it circular to say, okay, we can use it because of the invariance, and then later say, oh, and now it's invariant because we use that?
I'm not seeing the reasoning.
We using the same equation was because of the
Yes.
invariance, and then later on,
Yes.
what you're saying now is because we're using the same equation and not some r prime.
No, the statement that I make is that the same equation can be used. Yes. I'm not fully understanding what the question is. I'm using the same equation. I can. Because the equation holds in a particular coordinate system, as long as I'm not leaving the coordinate system, I can use the equation.
Yeah, no, I don't mean that.
I have a follow-up question also.
Would it be okay if I, for the sake of, just to have a rounded off story, interpret this equation just for a second, and maybe some of your questions will be answered, because I feel that it has to do with something that we can extract from the resulting equation. Of course, is the equation still linear, we're going to take it to the tutorial, okay? But just to get a nice rounded off story, let's interpret the equation in the red here. The question is valid, absolutely true. But again, short answer is we have not moved coordinate system.
It's like we're looking at two particles from the same point of view.
Yes.
Like those two people don't need to be observers, but just
Exactly,
particles.
yes. So no trouble there. Now, this equation tells you the general time dilation between one person and the other person. And now you can do fun exercises. You can ask yourself, well, who will see the most time between the two moments of it going through the orbit? Now, suppose that this number comes out, this square root comes out as a positive, or number bigger than 1, I should say. What does it say about d tau b compared to d tau a? If the right-hand side happens to be such that it's bigger than unity.
Now, observer B measures longer
Well,
directions.
yes, if the equation, the square root, happens to be such with the numbers put in that it's bigger than 1, then it apparently means that d tau b is a bigger number than d tau a. Okay, what does it mean about amounts of time? This guy goes from here to here, and it's measured by the person himself, that's the b time, and that's a bigger number in our example than this guy measures. Who sees the guy go faster to his orbit? Is that the A person or the B person?
B.
I hear A and B, so which one is it?
Yeah, sorry, I was confused.
A sees B go faster.
Yes, why is that? That's correct.
B would be experiencing time dilation. Since it's close to the capacity.
Yes, but can you just put it in pure mathematical terms alone?
Oh, because then the fraction will have a higher rate.
For the same distance traveled, B experiences more time. Hence, the change of distance over time.
Exactly.
Because
I mean,
velocity is slower for B.
That's all correct. I mean, it's completely fine. And by the way, the time dilation argument is good too, but the time dilation is something I would like to conclude based on the mathematics. But you're right. I mean, if you go from this point to this point, and in our example we saw that person B thinks that it takes more seconds to go from here to here than this guy does. Then this guy apparently sees person B move faster through his orbit than he himself sees. Do you agree? Right? If you ask person B, how long did it take you to take one full revolution, he says 5 seconds. And this guy says, no, I saw you do it in 3 seconds. Then person A apparently finds that person B is moving faster. So you can clearly see some time dilation. By the way, this square root, there's two numbers that you subtract from each other. Now, there will always be a positive number, I would say, yes. But will it always be bigger than 1? Can you make a situation where it's smaller than 1, where the opposite conclusion holds?
You need negative radius and negative mass.
Is that true?
Negative radius.
I'm sure you can make this smaller than 1 in one particular way.
If RB is bigger than 2 or smaller than 2, no?
At the very least, what you can see is that this particular time dilation depends on 2 effects. One of them, right, there's 2 terms in the total time dilation that we have here, 2 effects. One effect has to do with, well, apparently how close you are and how big the mass is, yes? The bigger the mass, the bigger this effect. On the other hand, there's also a velocity dependent part, how fast the guy is moving. So there's 2 contributions to the total time
Like the
dilation.
special relativistic time dilation.
Yes.
General
Yes,
relativistic
let's make,
time
yes,
dilation.
exactly. You already knew from special relativity that there already is time dilation if you have a relative motion with respect to each other. That is this one, because omega is your relative motion between person A and person B. Agreed? This is how fast they are moving with respect to each other. But now what you see is that there is, so that's an effect that you already knew from special relativity, and it's still retained in our expression here. But you see an extra effect here that has to do with the mass. You have an extra amount of time dilation here that is due to 2m over rb. Let's make the mass 0. Let's do that for a while. Let's look at a special situation here where you say, you know what? Let's look at the situation where there happens to be no mass in the middle. Physically, that means that there is a guy B orbiting, going into some circular orbit. It's just there's nothing in the middle. It's just a guy who happens to enjoy walking in circles. Okay? If m is 0, do you remember what happens if you put m as 0? What happens to the full space-time? Okay, so what would you expect if you make a situation where you're back in the Minkowski space-time? What kind of time dilation would you expect?
Lorentz factor.
Just normal, special relativistic Lorentz factor, yes? Let's see if that happens.
You just get to 1 minus the angular velocity times the radius, which is the right.
It is. Yeah, yep. That's it. Maybe you remember from classical mechanics that angular velocity and orbital velocity, so how many angle you're traversing per second and how many meters you're traversing per second, are related in exactly this way. This is not relativity, this is Newtonian physics that I'm going to put in. This particular combination is how fast you are moving in this direction.
We have the radius of B, but we have the angular velocity that A is B. So
Yes, I agree. I agree.
oh yeah, because B doesn't see any angular velocity, so it makes sense to use.
So what I get here is that d tau A you get this. Do you agree with this? Doesn't it look like time dilation to you? Especially relativistic time dilation.
I mean, c squared is 1. So
Yes, c squared is 1. If you put the c in, you would have gotten it here. By the way, remember from special relativity where you put the gamma. Time dilation for special relativity tells you that dt is gamma d tau. And do you remember what d tau was?
The B, because he sees two events
The
happen.
guy who sees two events happen at the same location. Is that person A or person B in our exercise? That's person B. So we get exactly the d tau at the right location. So we actually find now that our solution here has all of special relativistic time dilation encapsulated. Because you were the guy who brought that up. You said you have two time dilation effects here. This part is special relativistic. You have an extra contribution due to the presence of mass. From now on, we are going to call that the gravitational time dilation. The smaller m is, the less that effect. Or, sort of the same statement. The further away you are from the black hole, going away from the black hole means that this becomes negligible. You also don't see that effect. So apparently there is something called gravitational time dilation. It depends on how much mass there is, and the effect becomes really, really, really big if you get very close to the black hole. That's what it says here. Okay. Some lingering questions about invariance, but let's take those to the tutorial. Any questions about this particular derivation? Good. Okay, then I will see you at the tutorial. It is beautiful, right? You get your beautiful Minkowski effects back plus extra.
But special relativity, what does it just pop out?